Jai Hind everyone, I am Ankita Sharma, working as an assistant professor in Ajay Kumar Garg Engineering College. Today we are going to cover the complex topic number 4 of subject Microprocessors and Microcontroller, KEC 502, and the topic number is 8086 Architecture. So first of all, what is 8086 microprocessor? Microprocessor, we all know microprocessor is a programmable device which we work. So overview and features of 8085. So microprocessor 8086, my features of 8086. So 8086 microprocessor is an 16-bit microprocessor that works internally. It has internal registers. It works in 16 binary word, and 8086 has a 20-bit address bus and 16-bit data bus. Unlike in 8085, if I compare 8085 and 8086, 8085 was having data bus of 8-bit and address bus of 16-bit. But in 8086, the address bus is of 20-bit and data bus is of 16-bit. So here, 16-bit microprocessor, it has its ALU, internal register, that work in 16-bit. All these are of 16-bit. So 8086 has 20-bit address bus. So 20-bit address bus means if I have to count the memory locations, so 1 MB memory locations, we can count it by 2 raised to power n, which will be equal to m. Here n will be equal to our number of address buses. In 8085, if we remember, in 8085, the address buses were total 16. In 8085, it was 16 address buses. So it was 2 raised to power 16. It came up like this, or we call it 16 KB memory. This was the memory size for 8085. But in 8086, it will be like 2 raised to power 20, which is equal to approximately 10 lakh 80 or 45,874 or something. So lump sum it is 1 MB. This much memory locations are available. These memory locations are available. 1 MB for 8086. So this is a memory location for 8086, and it can support up to 64K input output ports. So input output ports, earlier it was of 8-bit or 16-bit, and depending upon that, there were 2 raised to power 8. It was 256 input output ports in 8085. But in 8086, we have 64 KB input output ports. So this much ports are there, and it provides 16-bit register. All the registers here are of 16-bit. In microprocessor 8085, we have 8-bit general purpose registers, and if we have to transfer the data, we have to carry the address. At that time, we have to combine the registers. We have to make the pairs in 8085. But in 8086, the register itself is of 16-bit. So no need to pair them. They are already of 16-bit. So frequency range is from 6 to 10 megahertz. And it has multiplexed address and data bus. Just like in 8085, 8085 was having the address and data bus multiplex, that was from AD0 to AD7. But here it is having from AD0 to AD15. We have all the data bus multiplexed with the address bus. And the 16 address buses are multiplexed with this address and data. And remaining 4, that is 16, 17, 18 and 19, these are not multiplexed. These are independent from the data bus. And the single phase clock here is used, which is giving 33 duty cycle, 33%. So this is the architecture of our 8086. So there are multiple blocks here, multiple features it is having. From here we'll be getting the data or the address, whatever. From memory and input and output. So the 8086 architecture is divided into two units. First one is R and next one is our EU. BIU is simply bus interface unit and EU is our execution unit. So these two are units, these two are our blocks. Our block is divided into two parts. This architecture divided into two parts, bus interface unit and execution unit. So bus interface means all the interfacing related done with the BIU and all the execution done with execution unit. Suppose we have to collect data from some address and we have to carry that address, that number. So BIU will deal with the outside world. We can say in simple words that BIU interface will deal with the outside world. From this point, it will carry the data and it will take this data to this instruction queue. Now this instruction queue plays a major role in 8086 architecture. It helps in speeding up the microprocessor. The microprocessor is very good in terms of speed here. So this is our instruction queue. This is our instruction queue. Instruction queue is of 6 byte. It can have 6 bytes of data in it. One by one, all the data will go from here. All the instructions will go on and it will operate on the function first in, first out, FIFO. It operates on the function first in, first out. This is first in, first out. Suppose the instruction come here at number 1, then 2, then 3 like this, and the number 1 will go out. After that second, after that third. So first in, first out. Whichever instruction will come first will go first out. So this is the working of this instruction queue. Why this is done? To speed up the process so that the microprocessor can work faster. It can multitask, you can say. And here one more important thing, this BIU and this EU, this execution, both these units work together. They work together simultaneously. It is not like that unlike in 8085 that we have to we have to fetch the data, then it will decode it and after that the execution will be done. No, it is not like this in 8086. While the fetching is done, that fetched instruction will go to the execution unit. That first instruction. When the first instruction will be executed, at that very time, the second instruction will be fetched. We'll discuss this in next slide now. So here we are having registers. These are 4 segment registers. We are having 4 segment registers and 1 special instruction pointer. So these are 4 segment registers: code segment, data segment, stack segment and extra segment. These 4 segment registers are used here and this is our instruction pointer and this is a summation which is used to calculate the physical address of any instruction. In 8086 the address is directly not find out. It is not directly given. We have to derive it from different registers. Some part will be given in the segment register. We'll be multiplying it with 10 and the offset of the address will be given to us. It will come like a numerical lately. So these are general purpose registers. It is having 4 general purpose registers. A is for accumulator, B is for base register, C is the count register and D is our data register. These 4 are general purpose registers and these 4 are divided into 2 parts. Accumulator lower part, accumulator higher part. Each of them is of 8 bits. 8 bit each. 8, 8, 8, 8, 8 and 8. Suppose I have to, the microprocessor have to carry the data which is of only 8 bit. At that time, this can be used. If the 16 bit is required, then whole accumulator will be used. The lower part of the address will be stored in the lower accumulator or lower part of these registers, and the higher part of the register, higher part of the address will be stored in the higher register. Next is our stack. These two are our pointer registers. These are pointer registers. One is base pointer and second is our stack pointer. Stack pointer and base pointer. These are used to point the stack. Stack pointer, base pointer. And these two are our index registers. Index registers, one is source index and next is our destination index. These are our index registers. And here in execution unit, it is control unit. All the transferring, everything which is done in microprocessor 8086, whatever the function is going on is done by the control unit. You can say it is a brain. It is controlling. It is controlling it. Here ALU is arithmetic logical unit. All the addition, multiplication, subtraction, increment, decrement, XORing, logical operations and everything is done ALU. Here we are having some operands which we'll be using and flags. Flags are our flag registers. So this is the basic of architecture, and now we'll be just discussing the execution part here. How this instruction queue works. Suppose the microprocessor is fetching instruction. It is fetching instruction. It is fetching instruction and this instruction has gone for the execution in execution unit EU. This was done in BIU and this is done in EU. While this instruction is executing, at that very moment, second instruction will be fetched, F2. Simultaneously, this will be done in BU and this will be done, this will be done in BIU and this will be done in our EU, execution unit. Similarly, when this will be done, this instruction will be sent for the execution. Second instruction will be executed and then third will be fetched. Same, when third will be executed, then what will happen? The fourth will be fetched and so on till halt comes or the program finishes. So this is the basic funda of instruction queue and pipelining also. You can say pipelining. How this is done through pipelining. One after the other things are going on in a parallel way, not in a serial communication. No, not serially. These are performing in parallel. This function and this function, these both are in parallel process. This is in parallel process. Simple. In 8085, it was like this. First instruction was fetch. It was executed. When it was executed, microprocessor was free. Then the second will be fetched. After that, it will be executed. After that, third. After that, third will be executed. So this was serial. It was done serially. And this is parallelly, or we can say pipelining is done here. So why we have discussed this BIU and EU, execution unit and bus interface unit. BIU is that is performing all the bus operations like instructions, fetching, and we have to write the operands, we have to read the operands from memory and interface them through the outside world or the addresses. And here execution is used to execute it. It takes the instructions or data from the instruction queue. So these units work asynchronously. It doesn't mean that they will start together and they'll just stop together. They'll work asynchronously to give 8086 and overlapping instruction fetch and all that. So BIU contains the instruction queue, segment register, instruction pointer and adder, which we have just discussed, the physical adder. And execution unit controls is having control unit, it is having ALU, it is having operands, it is having index registers, flag registers, general purpose registers and different source index registers also, pointer registers. So 8086 has two parts, bus interface unit, execution unit. It reads and writes data, computes with 20-bit address. We'll be just finding out how the physical address will be done lately. So these are the segment registers or the registers. Execution purpose. So instruction pointer, code segment register, data segment register, stack segment register and extra segment register. These all are the segment registers which are used to find out the address of that instruction. So now BIU can be used to fetch the instruction using code register and instruction pointer, and it can be used like this. The code segment address is written and instruction pointers is given, which is called the offset, and we have to make this 20-bit address, which is called the physical address of the instruction. When the data is fetched using this segment register, usually we use the data segment register, and the effective address is given by the addressing modes. So these blocks we have discussed just now: the accumulator, AX, base register, count register, data register. These are our general purpose registers. These are pointer registers, and these two are index registers. These are referred to as general purpose registers, all these, and these are special purpose registers. So same thing, AX, BX, CX and DX can be considered as two 8-bit registers, and when they combine they are 16-bit. Two 8-bit means higher byte and low byte, like this. We have seen this already in the architecture as well. So this is the 8086 programmable model. So programmer's model is this. If in exam, if the question came like, explain the 8086 programmer's model, only programmer's model, then we'll be doing this. And if it is the architecture of 8086, then we'll be covering this. This is the architecture of 8086, the fully block diagram architecture you can say, or we can also call functional block diagram. Functional block diagram. This is functional block diagram or architecture. And if the programmer's model is asked, then this is the programmer's model. So programmer model is having the segment registers and instruction pointer and all the general and special purpose register. That's it. All the registers given here, these all are our programmer model. So this in combination make the programmer's model, and everything is we have discussed earlier. So these are our flag registers. Like in 8085, the flag register generally just contain the information that reflect the current status of the microprocessor. What is microprocessor exactly doing? What is the current status of the microprocessor? How the accumulator is behaving? What is the behavior of accumulator depending upon the registers? So in 8085, we were having 5 registers: sign, parity, 0, auxiliary carry, and carry flag. So these 5 registers were there in 8085, and these 5 these 5 same flag registers are also given in 8085 till here. If we closely look till here, so bit number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So flag register is of 16-bit. It is also of 16-bit. At that time, from 0 to 7, this sign, 0, auxiliary carry, parity, carry. These 5 flags are same as it is as they were in 8085. The placement is same. The working is also same. They serve the same purpose as they were serving in 8085. Sign flag tell the status of the microprocessor, if it is having positive sign or negative sign. Sign flag. 0 flag, auxiliary carry and parity. And these 4 flags are in addition in 8085. So 4 flags are trap flag, interrupt flag, overflow flag and direction flag. These 4 are our flags that are different in 8086. So in 8086 we are having total 9 flags. So 9 flags are also categorized in 2 parts. One is our control flags and status flags. So we are having 6 status flags that tell the status of the microprocessor and 3 control flags. So 3 control flags are these control flags: direction, interrupt and trap flag. These are our control flags, and remaining 6 are our status flags. So status flags will be our overflow flag, sign flag, 0 flag, parity flag, auxiliary carry flag and carry flag. So let's just discuss these one by one. So first of all, carry flag. Carry flag is used to signify whether there is a carry in the MSB of the answer or not. Suppose it is of 16-bit. So the after 16-bit, if there is some 17th bit, that will be our carry. If that is there, it will be 1, otherwise 0. Parity, if the answer, the parity, the number of ones, parity shows the number of ones. If the number of ones is even, then it will be even parity. And if the number of ones is odd, then it will be odd parity, means 0. This is auxiliary carry flag. When the carry is going from lower nibble to higher nibble, which is used in 8-bit operations only, at that time auxiliary carry flag will be active. So from D3 to D4, if a carry is going, at that time auxiliary carry flag will be active. 0 flag is if the whole answer is 0. Suppose we are doing a subtraction and we are doing a subtraction from 1a minus 1a. Suppose I am doing this 1a minus 1a. It will be 0. Active. Active means it will be 1. If the result is 0, then 0 flag will be 1. If the result is not 0, it is not equal to 0. If the result is not equal to 0, at that time 0 flag will be 0. It is reset. So this is sign flag. Sign flag, if the result is negative, at that time 1. If it is positive, 0. Next is our trap flag. 1 if it is performing single stepping. It is not using multi modes. Like in 8085. 8085 is having different modes, maximum mode and minimum modes also. If it is not doing that, it is performing single step, then it is trap. It is not performing single stepping, it is not trap. Interrupt flag is there is any active interrupt. Interrupt is enabled, this flag will be active, high. If it is not, then it will be low. Next is direction flag. If the direction is auto decrement. Auto decrement means the numbers are decrementing. Decrementing means like from 10 to 9, 8, 7, 6, 5. These are decrementing. Then it will be 1. If it is incrementing like 0, 1, 2, 3, 4, 5 in a sequence and it is incrementing, at that time this will be 0. Overflow flag, if there is an overflow after this, at that time the numbers will be overflowing. It is used for signed number. Suppose we are adding two positive number. If an overflow of number is there, at that time it will be count as overflow. And if we are using two negative numbers, at that time also the signed number will be overflow. So these are the flag registers. It contains a group of status bits that are called flags that indicate the status of the CPU or the result of our ALU, arithmetic operation. We are having two type of status here. We are having two type of flags here. One is our status flag, one is our control flag. Status flags will reflect the result of executing an instruction. The programmer cannot set or reset these flags directly. We cannot change these flags according to our wish, according to our convenience. No, the status flags will be directly set or reset. That can be done only by the microprocessor itself. These control flags can be enable or disable certain, it can enable or disable certain CPU operations, and the programmer can set and reset these bits to control the CPU's operation. We can set them according to our convenience. So there are 9 individual bits of status registers. 3 of them are control flags and status flags are 6, and remaining 7 are not used. We can say it don't care. We don't care what is the bit at that time. So a flag can only have value 0 or 1. If it is set, it will be 1. If it is reset, at that time it will be 0. So 3 control flags are there. Direction flag, it affects the direction of moving data blocks. By such instructions, suppose we are moving these instructions, moving, complement and these. So these are the registers. For up, it will be 0. For down, it will be 1. Interrupt flag is used for the interrupts. If the flag is 0, that means the interrupt is disabled. If it is 1, that means the interrupt is enabled. This is our trap flag. When this flag is 1, the programmer can single step through his program to debug any errors. And if it is 0, then it is off. We cannot debug the error. So, carry flag, we have discussed earlier also. If it is 1, there is carry. If it is 0, that is not carry. Overflow, if it is 1, there is overflow. If it is 0, there is no overflow. Sign flag, if the result of the MSB is positive, it will be 0. If the answer is 1, it will be negative. 0 flag, if the total result is equal to 0, this will be set. If the result is not equal to 0, it will be reset. Next is auxiliary carry flag. When the answer is having a carry that is occurred in between the bits from D3 to D4, this carry is auxiliary carry. Parity, the number of ones in the result. If the number of ones is even, like 2, 4, 6, 8, 9, 8 and 10, 12, at that time the value will be 1 for even and the value will be 0 for the odd numbers. Thank you.